what I want to talk about, that's a little loud. What I want to talk about today is twisting, which means passing from representation theory well, anyway, that's related to some connected G, passing to representations of some disconnected I guess well, this is going to be generated by G and delta, and well, so for us, always this delta squared is going to live in G, and so this group has exactly two components, and well, so the first thing I want to do is explain why it's a perfectly natural thing to think about representations of disconnected groups, and that's something that well, might be a good direction for Atlas to expand, but what's going on here is we're taking the point of view that all we care about is the representations related to a connected group, and nevertheless we're forced into questions about this disconnected group. So let me begin. Well, no, let me first say we have always a real form, G of R, and always that's the fixed points of this anti-holomorphic involution. I guess I'll just call it sigma, from G to G, and the way the structure theory works is that remember we find a compact real form. Well, so sigma C mapping G to G, so that if you take the real points with respect to sigma C, you get a compact group. And the requirements are that these two involutions should commute, and we'll call their product in either order that this is the Cartan involution. And well, I won't go through all the wonderful structure theory that this gives, but let me just say that we want to study well these GK modules M with an invariant Hermitian form, and what the invariance condition means is that if I take an inner product like this, sigma of C and 2, I'm writing it in. This sum is 0. So usually what happens is that people just look at this equation for Z in the real Lie algebra, and well, and if Z is in the real Lie algebra, you can omit the sigma. Well, because it's fixed, but we're taking this strong point of view that complex is better, that always we should have in mind just an action of the complex Lie algebra, and so I want to write the condition like that. And well, so here's a stupid example. Let me take M to be the 5-dimensional irreducible representation of SL2R. And the question is, well, so I like to write it like this. These dots are supposed to correspond to the SO2 weights in the representation, and the question is, well, this is an orthogonal decomposition for this invariant form, and we want to know what the signature looks like in this picture. And I explained an argument, a deformation argument, which told you finally that you could make the signature look like that. I want to look at this in a different way. So here's an alternate approach, and I mean, we need this for general G. I mean, I did a lot of hand waving about a number of things in the case of SL2. It's all true and okay, but for general groups, we don't. I'd say what's true is that we don't know how well, I'll say study the deformation of invariant Hermitian forms. The words that I said about the subject were all true, but carrying everything out in detail, we just don't know how to do it. So we need this cleverer approach, which is, this is in the slides from yesterday, a C invariant form. I'll put a superscript C. Well, the defining property is not what's ZM1 and M2, the C invariance plus M1 sigma c of z at M2 is 0. So almost exactly the same, except I replace the real form that I've got by this different real form. So this is perfectly legal. We're still talking about GK modules. This is a perfectly legal definition. People didn't make it in general because it seems sort of irrelevant to G of R representation theory, but it's a legal definition. And in the case when M is finite dimensional, what I can do is choose this MC to be invariant for this compact form. Well, so in this SL2 case, we're talking about SU2. And the representation theory of compact groups is wonderful. The theorem is that every finite dimensional irreducible of a compact I'll just say a compact group. I won't give it a name because the only reasonable name for a general compact group is K, and we've wasted that already. Has a positive definite invariant Hermitian form, which is unique up to a positive scalar. Great. So Jeff doesn't want me to use other colors, but I'm going to write in the sigma C invariant form that has signature pluses all the way along. So no long, complicated deformation argument. This is just all pluses. Great. So the question then is, well, what I want to do is relate this C invariant form to the invariant forms that we want to study. And so the obvious theorem is that a GK module M has both a C invariant and an invariant Hermitian form. Well, let's say irreducible. Doesn't matter, but if and only if there's an operator T from M to M whose Hermitian transpose with respect to the compact form is T. And what's required is, well, So, well, I don't know. The ordinary form, it is M1 TM2. So again, it's a familiar idea from linear algebra that, I mean, I'll just write it briefly and I'll erase it. That forms, well, maybe it's most familiar in the world of quadratic forms, say on Rn or something, are in one-to-one correspondence with symmetric matrices T, so the form, well, it is just V1 TV2, and this is the Rn inner product. So once you've got one non-degenerate symmetric form, you can write all the others just by twisting that one form by T. So here, once I've got a C invariant form, I can get my invariant form by twisting it by some linear operator. And if you look at these conditions, well, sigma C and sigma differ by theta, and well, so you're led to this. So all right, so what we have to do is I need to find an operator T on this, for example, 5-dimensional space with the property that well, and here theta of Z is minus the transpose of Z, and this is supposed to be for any Z in the Lie algebra of SL2. And this is easy to do. What you do is, let me write pi is this, well, representation of SL2C, and I'm going to take T to be pi of 0, 1, minus 1. Now yeah. Well, the point is that one of the things that we saw in the discussions about KGB and so on, it is that the adjoint action of 0, 1, minus 1, 0 on a matrix in SL2 is the negative transpose. As soon as I write that, I feel good. Thank you. Good. Okay, so what's going on? The point is that to get the signature of this invariant form, this is it's basically just this signature of the C form, and it gets multiplied by the eigenvalues of T. And this 0, 1, minus 1, 0 is in SO2, and so this acts on the K weight space by I to the power K. And so, well, in this minus 4 to 0 to 4, I'll write down the powers of I there like that. And that's how the red arrows get changed into the red pluses get changed into the black plus or minuses. So, wonderful. This is not rocket science, and I'll tell you historically. So around 2012, this atlas knew how to compute the signatures of these C invariant forms on the M where they exist. And well, when theta is inner, it corresponds to just the adjoint action of some x. I mean, that's what happened here, and so you just actually this x is necessarily in the center of K. If the adjoint action of x is going to define the Cartan involution, that that's what I said, that was theta. The Cartan involution is trivial on K, so x should be in the center. And so you take, you modify the signature of this form on the representation tau of K by the scalar tau of x. It's a central element. It acts by scalars. That's the argument. And so we were able to compute signatures in the equal rank case. Well, as I say, when theta is inner. And so that's, I forget how long ago that was, it's somewhere in there.
And so the general case should just be a small tweak of that.
Nothing to it. So
this theta relates to the composition of sigma.
yeah, see that's the definition of the Cartan involution. Is you've got this real form sigma, you pick a compact real form that commutes with it, and then their product in either order, well, each of them is anti-holomorphic, so their product is holomorphic, and that's the definition of the Cartan involution. So this is probably about the 100th anniversary of the definition of the Cartan involution. So actually, probably we should have celebrated it on Bastille Day or something. But so yeah, if this thing is inner, then it's all wonderful. And So in the general case, more or less, you need to extend this GK module to a G, we write K delta module. So remember that Atlas uses this extended group I'm not going to recall everything about it, and this theta is represented by some class X is G delta, and so this K delta is by definition the centralizer in this extended group of this element X. And so it has X in it. And in fact, it's kind of obvious that K delta is generated by K and X. Great. Then, well, once M is extended, then this operator T is just essentially the action of this extra element X. And this let's see, the thing to notice, yeah, that this X is central in K delta, and so this is a scalar on each irreducible of well, K delta. And same thing is here. You just take the sigma C invariant form that we already knew how to compute, and you twist by these scalars. Okay, so what this says, so
Can I?
Sure.
Yes, just make sure.
Sure.
I got it right. So we treat each in a class separate.
Yes, absolutely, absolutely. When you're doing this, this delta corresponds to the inner class.
When you say that you know what to do for the equal rank case, you mean that you know what to do for any group for the inner class to be open.
That's exactly right. Equal rank means in the inner class of the compact group. And well, of course, now we know what to do for any case, but
So you just need one evolution, one after.
yeah, piece of cake. So, okay, so how does this work? So I want to talk about the case of finite groups. Yeah, so the problem is to extend this theory of GK modules to a theory of this G K delta modules. So let me talk about the sort of toy example. So I'm going to start with a finite group, and this is contained in some larger group that I'll write G delta, and I want this to be index 2. And I want to understand the relationship between the representation theory of G and the representation theory of G delta. This is old news, you know, but I just want to review the obvious facts about this. So the first thing is that delta acts on the conjugacy classes. Sorry. How should I say it? Let me say G delta over G, which is this two-element group. I don't know. I'll screw up the notation. This thing acts on, I'll write G for the conjugacy classes in G. And so we have A fixed points and B orbits of order 2. If you have a group of order 2 acting on a set, there are fixed points and there are two-element orbits. That's all there is to it. And so the total here is A plus 2B. And it's also true that this G delta over G acts on G hat. And so again, there are fixed representations, and there are pairs that are interchanged.